All right, let's talk about concrete, specifically how we design with it. Today, we're going to build a really practical roadmap for designing two of the most common things you'll ever see in a structure: concrete beams and one-way slabs. And we're going to do it all following the rulebook, ACI 318-19.
I mean, think about it. We trust our lives to concrete every single day. The buildings we work in, the bridges we drive over, the very floor under our feet. So, how do we know it's actually safe? What's the process for making sure these structures can handle all the stress we put on them?
Well, the answer lies in a massive, incredibly detailed rulebook. For us here in North America, that's the ACI 318 code. You can think of it as the Bible for structural concrete. It lays out the absolute minimum requirements to make sure our designs are safe, strong, and gonna last.
So here's our game plan. We'll start with the code's basic philosophy, then we'll get into the nitty-gritty, loads, and how we analyze for them. After that, we'll walk through designing beams, then see how those same ideas apply to one-way slabs. And we'll finish up with two crucial pieces: how to detail the steel reinforcement and the role that you, the engineer, play in all this.
Okay, first things first. You gotta understand what the code is and what it isn't. ACI 318 is not a cookbook that gives you all the answers. It's a foundation. It provides the minimum requirements for a safe design, but it absolutely relies on you to bring your professional knowledge and experience to the table.
So every single design, no matter how simple or complex, starts in the same place: the loads. What forces is this thing going to have to resist? We have to account for everything: the structure's own weight, the people walking on it, furniture, snow, wind, you name it.
And to be safe, we don't just design for the expected loads. Nope. We design for the worst-case scenario. The code makes us use these factored load combinations. We take the dead loads, D, and the live loads, L, and we multiply them by factors, like 1.2 and 1.6, to build in a margin of safety. The biggest number we get from all these combinations becomes U, our required strength. That's the target our design has to beat.
Now, once we have our loads, we have to figure out how the structure responds. And here's a key thing: concrete cracks under load. It's not perfectly rigid. To account for this reality, the code tells us to use a reduced stiffness in our analysis. For a beam, for instance, we're told to only use 35% of its full stiffness, its gross moment of inertia. This gives us a much more accurate, much more realistic model of how the forces will actually flow through the cracked structure.
All right, let's roll up our sleeves and actually design something. We're going to tackle a standard, non-pre-stressed concrete beam, following the workflow from Chapter 9 of the code. It's a really logical, step-by-step process.
It really just boils down to three main gates you have to pass through. First, you do a quick reality check on the beam's dimensions to make sure it's not too flimsy. Second, you calculate the required strength, that U value we talked about. And third, you design the steel rebar that's going to give the beam the muscle it needs.
That first check is a real time saver. The code gives us these simple span-to-depth ratios. For a simply supported beam, for example, as long as its depth is at least its span length divided by 16, we probably don't have to do a super complicated calculation to check for sagging. It's a fantastic rule of thumb to keep our floors from feeling bouncy.
Now, this right here is the heart of the entire code. I'm not kidding. Everything comes down to this one simple inequality: design strength must be greater than or equal to required strength. The capacity has to exceed the demand. Our design strength is the theoretical strength of the beam, S sub n, multiplied by a strength reduction factor, phi. That little phi is our built-in safety cushion. It accounts for all the little imperfections of the real world.
So you might be thinking, what if my calculations show I hardly need any steel at all? Well, the code says, not so fast. It requires a minimum amount of reinforcement no matter what, and the reason is so important: ductility. Without enough steel, a concrete beam could fail without any warning, just snap like a piece of chalk. But with that minimum steel, it's designed to bend, sag, and show huge, obvious cracks long before it fails. It's designed to scream for help.
Okay, let's switch gears to one-way slabs.
The great news is, if you understood how we designed that beam, you're already 90% of the way to designing a one-way slab. Because, as we'll see, a one-way slab basically just acts like a really, really wide, shallow beam.
But first, a quick but important distinction. A one-way slab is supported on two opposite sides, so it bends in one direction. A two-way slab is supported on all four sides, so it bends more like a dish. They're designed differently. For this explanator, we are focusing only on one-way slabs.
So what's the trick to designing this big, wide element? We simplify. We basically imagine slicing the slab into a bunch of 1-foot wide strips, all sitting next to each other. Then we just design one of those strips as if it were a rectangular beam that's 12 inches wide. All the same rules apply: capacity versus demand, minimum steel, it all works.
And just like with beams, slabs have a hard and fast rule for minimum reinforcement to ensure they're ductile. For a slab using grade 60 steel, the minimum area of that steel has to be at least 0.0018 times the gross area of the concrete. It's a non-negotiable check you have to make every time. Now, here's one place where slabs are different from beams. Because slabs have such a huge surface area, they're really prone to cracking as the concrete cures and shrinks, or as the temperature changes. So the code makes us add another layer of steel perpendicular to the main reinforcement. This steel isn't there to carry the primary floor loads. Its only job is to control those temperature and shrinkage cracks.
Look, a design is more than just a bunch of calculations on a page. It has to actually be buildable. This is where the rubber meets the road. Detailing the reinforcement correctly is what makes sure all that steel we designed can actually do its job in the real world. And one of the most critical details is something called development length. Just think of it as grip length. It's the minimum amount you have to embed a bar into the concrete to make sure it's properly anchored. If the grip length is too short, the bar will just pull out when it's loaded, and it becomes a completely useless piece of metal.
And figuring out that grip length isn't just a guess. The code gives us these pretty intense equations. Now, you don't need to memorize this, but look at what goes into it. It depends on the steel strength, the concrete strength, the size of the bar, even whether the bar is coated. It's a precise calculation that ensures every bar is properly anchored to do its job.
Which brings us to our final and maybe our most important point of all. We've walked through the rules, the processes, the equations, but the code itself is only one half of the story.
And don't just take my word for it. The code itself says it best, right there in the commentary. It's a powerful reminder that ACI 318 is a fantastic guide that sets the minimum bar for safety, but it can't possibly know the unique conditions of every single project. That's where you, the engineer, come in.
So here's the big takeaway. The code provides an incredible, essential process for ensuring safety. It gives us the framework, but it's the engineer's expertise, their critical thinking, and their professional responsibility that turns that framework into a safe, real-world structure. It's a partnership, which leaves us with the ultimate question for every engineer on every project. Where do the rules on the page stop, and where does your professional judgment have to take over?